Hello everyone, my name is Pablo Collantes and I'm from the University of Texas at Dallas. Today I'll be presenting my summer research project on a predictive approach to monitoring and detecting failures in robotic systems. So first, I want to talk about the need for proactive safety in robotics. Modern robotic systems can be simplified and displayed kind of like a stack of interdependent layers from the physical hardware at the core, and then you have perception and state estimation, planning and control, and at the very top, safety and monitoring. So yeah, a failure at any of these levels can lead to a significant safety issue or hazard, especially in critical applications like autonomous vehicles or robotic arms, and in these industrial and medical settings. So the core challenge is that a failure often develops silently before it results in a measurable error. And this kind of shows a critical need for a system that's not just reactive, but also proactive. Something else I also want to highlight is a new and emerging vulnerability called cyber-physical inconsistencies. This is where most of the challenging failures can often occur, which is right between the cyber and physical domains. So you can see in the figure on the right, the physical domain is continuous. There is no solid line that will clearly declare an anomaly in the robotic system. However, the boundary in the cyber domain must be distinct. And that can then create inaccuracies where the monitor, on monitoring the robotic system could maybe have missing exceptions in an under approximation is where the software could provide and allow a perfectly logical command that would be to the software side, but this could create a physical issue or error to the real robot. And on the other side, we can have over approximations where the cyber domain is very cautious and the line is set too far below, and this will create a lot of false alarms. And so this concept of the cyber-physical gap and this new vulnerability of cyber-physical inconsistencies highlights the difficulty of describing and implementing physical boundaries within software. So now I want to evaluate current runtime monitors and also their limitations. So for one, existing runtime monitors typically focus on a single layer, and this can create blind spots within the robotic systems. So first, there'd be physics-based monitors, and these would be using sensor thresholds. So for example, this could be temperature sensors, motion sensors, or force limiters. And the issue with physics-based monitors is they can't understand the software's intent. For these sensor thresholds, it would be able to detect, for example, an overheating motor, but it wouldn't be able to tell what had caused the overheating motor, whether it was a malicious command or a faulty plan, and therefore cannot diagnose the root cause and fix it in the future, or at least let it be known to the user. Next would be software-based monitors, and these use code assertions. So this is hard limits within the software for the robotic systems, and these are essentially blind to physical reality. These monitors will be able to interpret the bugs or error codes and faults from the robotic system, but it cannot detect physical degradation or environmental interactions like external forces to the actual physical model. And lastly, even sophisticated reactive controllers can only correct an error after it has already happened without diagnosing the underlying cause. So therefore, none of these can effectively address failures that emerge from the complex interaction between the software and the physical models. And so now this leads us to our core research questions that we have been trying to investigate for this framework. So firstly, it would be, can a predictive joint model framework provide better coverage for failure detections than these single layer monitors by trying to cover this cyber physical gap between the software and physical monitors? Next, how can we build an accurate and adaptive physical model using system identification that will be accurate enough and reliable enough to predict the real world robot's behavior? And then finally, can this approach effectively detect the vulnerabilities that we're trying to investigate, like planner errors, physical degradation, and external interference? So, to answer our first question, we propose our approach, the RoboTrace Joint Model Framework. And so, this framework, instead of waiting for an error, our project's goal is to look into the future, and using a joint model approach, the framework takes a proposed command from the robot's control system and it predicts the most likely physical outcome. Based on this prediction, it can determine if the action will be safe or if it would lead to a failure. And this allows the system to verify commands before execution, essentially closing the gap left by reactive systems and also single layer monitors like the physics-based monitors and the software-based monitors. And so this is handled by having our physical model, which is generated using system identification, and our computational model. This will then create our joint model combination here. And then during runtime, we use user-supplied objective functions, which will test and check the predicted steps on spatial and temporal rules, and then it will allow to see during runtime if the task and the command being sent is safe for the robotic system. Next, I will go a little bit more in depth into the RoboTrace failure prediction framework. And so at its heart, it's two models. The computational model, or CM, determines the ideal control command to achieve a task. But before that command is sent to the robot, it's fed forward into the physical model, or the PM. And so the PM acts like a digital twin of the robot's physics, predicting the most likely outcome based on the computational model's control input. And so this gives our system kind of like a short-term forecast of the robot's trajectory, which we can then analyze for potential problems within the task and detect whether it will be safe or not to continue. And so here in this diagram, you can see XT is our initial state of the system, and this is fed into our computational model and our physical model. The computational model is then used to control input, and this control input is then given to the physical model, which will then predict the next state, which is the XT plus 1, or the state estimation. And this can continue until either we have a 2 to 5 second sort of window predicting the next steps, or we can predict the entire objective and decide whether it is safe, a safe task, or if it was unsafe. And so, answering our second question on how to build an accurate and adaptive physical model, this system relies on system identification. And so, how it works is we start with the fundamental equations of motion and use real-world data to solve for the specific physical parameters of our robot. And so how it works is we know the fundamental dynamic model, say for a manipulator, a robotic arm, and in this equation, it is nonlinear, but we can arrange it into a linear regression manipulator equation, and then this equation would allow us to essentially more easily compare our initial command given to the robotic system, whether it be the manipulator or a more simplified robotic system, and compare that initial command to the actual output given by the robotic system. And then we'd essentially be training this physical model with the initial position, velocity, and acceleration data to the actual output from the robot, and then continue to train the physical model to then be able to have our digital model acting just as the real robot would act. And this is how you would be creating the digital twin. And so this linear manipulator equation for the arm and also the linear state space model It allows us to use this data of the initial command and the actual output to find the unknown physical parameters like the link mass, the inertia, or the joint friction after passing in the movement data, the real world data gathered in its motion. For other robotic systems like wheeled robots that function on fewer degrees of freedom, like on a single plane, they can be identified and their physical model can be predicted using the linear state space model. So the role of system identification allows us to create a physical model that is consistently tuned to our specific robot, as no two robots are exactly alike. Now I want to go over an implementation example for the data collection for system identification that we had done for a 6-degree freedom arm. And for the Robotrace predictive framework, all the robotic systems that we had worked with use a ROS2 framework. This is the robotic operating system. This allows all of the components within the robotic system to communicate with each other through a set of nodes. And so for the system identification of the arm, to build this model practically, the first step is high quality data collection. So we developed a ROS2 node that subscribes to both the plan trajectory from MoveIt2, and MoveIt2 is the external planner to the robotic system, especially for the robotic arm that we had worked with. And we also had subscribed to the real-time feedback from the robot's hardware. And so a key technical challenge here is that the planned motion uses relative time, which means MoveIt2, our external planner, starts its joint trajectories at t equals 0, while the robot's feedback uses absolute time, which means real-world time. Our node's primary job is to solve the synchronization problem by aligning these two data streams. This produces a clean, synchronized dataset of inputs and outputs, which is the critical foundation for our system identification algorithm. So next, I want to go over our experimental validation and our platforms. So to validate our approach, we are testing on both physical hardware, like the UFactory Lite 6 arm for the physical manipulator, and also the TurtleBot 4 for the physical mobile robot. And then we are comparing them with the high-fidelity simulated counterparts in the NVIDIA Isaac simulation. So for the simulated mobile robot, we are using the NVIDIA Carter, and then simulated manipulator, we are using the NVIDIA Franca. And crucially, we are using the simulation to evaluate the framework's performance across a variety of tasks. And this would be through complex manipulation like drawing to mobile robot navigation. And we'll also use the simulation environment to inject targeted attack vectors like command injection and parameter modification to prove that our framework can detect these failures. And now finally, to answer our third question, this joint model approach allows us to cover the blind spots that we identified earlier. And so within these cyber-physical failures, we are able to detect a faulty plan by predicting its unsafe physical consequences using the failure prediction framework and seeing it ahead of time before it's actually given to the physical robot. Next, it can identify physical degradation when the real robot stops behaving like its identified physical model. And finally, it can also provide defense against external attacks by verifying commands before execution and seeing if that command is faulty or can produce an unsafe situation. And so in each case, it's shown that the fusion of the software model and the physics model can help provide a more comprehensive and full coverage of these cyber-physical failures. And so in conclusion, while we are still in the process of final validation, our research presents a strong case for the value of joint model monitoring systems. And with this failure prediction framework, we can see how the joint model approach improves on failure detection by showing its potential to cover the cyber-physical gap left by single monitoring systems, and also by forecasting future commands within a task and evaluating whether they are safe or not. We can prevent failures proactively rather than just reacting. And by using an interpretable physics-based model, uh, this provides us better diagnostics and a deeper insight into the root cause of failures presented by the robotic system. And so this represents a significant step towards creating more robust, reliable, and trustworthy robotic systems. And that is it. Thank you.